where our discussion was in the previous class. I gather from your class rep that at some point I got disconnected. So my apologies, you were not able to get all the information. However, what I want to do is quickly run through the example that I was doing in the previous class, because it's very important that you start getting some of those concepts at this point. Now, remember, we were talking about how we are able to test whether any point that we are given on the S-plane lies on a root locus. And we agreed that there are two fundamental conditions that any point must meet for us to qualify it as lying on the root locus. The first condition was the angle condition. I think I mentioned that in the previous class. The angle condition is the condition that if you sum up all the angles of the points on the root locus, then it should add up to 180 degrees. That was our discussion. The other one was that the magnitude condition should sum up to 1. What that therefore means is that whenever we are testing for a point as to whether a point lies on the root locus, we start by testing the angle condition, because the true essence or the true purpose of the angle condition is to tell us whether that point lies on the root locus. But then we must also test it on magnitude condition. What the magnitude condition does is to give us the gain K at which that point lies on the root locus. So it's not just enough to note that the point lies on the root locus. We must also note the gain at that point, because as designers, we know that there are certain gains. Remember, we had said that the gain in root locus for our discussion would lie from any point between 0 and and infinity. So there are certain ranges of gain K that would make the system unstable. They might be lying on the root locus, yes, but the system would be unstable beyond those gains. So we have to know the gain that allows the system to remain stable, even if it lies within the root locus. Because the system could be the gain of that system could be as high as infinity, but it could at that point be seriously oscillating. So it is important for us to get the angle condition and the magnitude condition. And so quickly to the example that I gave, it was simply so this is what some books will call a feed-forward transfer function. A feed-forward transfer function, because we have a feedback transfer function also. So this is the feed-forward transfer function. So you're given the feed-forward transfer function. It consists of a 0 at -3, another 0 at -4. It consists of a pole at -1 and another pole at -2. So you can actually see that I have drawn the 0 at -3 and the 0 at -4. I have also drawn the pole at -1 and another pole at -2. We are to test whether the point, the question was, we consider a point -3 plus J3. So we have to, that becomes our test point, because it's the point we have to consider. So it's the point we have to plot on our S-plane, and you can see it is -2 plus J3. So we are asked that if this test point is a closed loop pole for some value of K, we must test it for both the angle and magnitude condition. That is, we know that if the test point -2 plus J3 lies on the root locus, then if we subtend all these lines to the poles and the zeros of our transfer function, of our feed-forward transfer function, then we should be able to add up these angles, and they should add up to 180 degrees. But if these angles don't add up to 180 degrees, then it means that this test point does not lie in the root locus. So if you subtend all the poles and zeros of the feed-forward transfer function to your test point and sum up all the angles they make with the real axis, then you should get 180 degrees. If you don't get 180 degrees or any odd multiple, remember we had said it should be plus an odd multiple of 180 degrees. So it could be 180 degrees. It could be plus or minus 540 and any odd multiple. So it's like This is 180 by 1. Remember, this is 180 by 3, an odd multiple. It could be again 180 by 5, you know. So anything that is an odd multiple of 180 is an acceptable angle. So in this case, because I'm just recapping what we did last time, if we subtend all these angles, I have named all the angles theta 1, theta 2, theta 3, theta 4. Notice all angles are measured from the real axis in the counterclockwise manner. So if you check theta 1, theta 2, theta 3, and theta 4, if we sum them up and they add up to 180 degrees, then it qualifies this test point minus 2 plus J3 would then lie on the root locus. If those angles don't add up to 180 degrees, then the test point minus 2 plus J3 does not lie on the root locus. That is the rule. So now, I also said at this point that once you find that the angle condition is not met, there's no need to test for magnitude condition, because it is the angle condition that must be met before you then move to the magnitude condition to get the gain. The essence of the gain or the magnitude condition is to give you the gain K. Okay, so in our case, we can test for theta 1. And you use your, of course, like I said, it's just important that you use your mathematical skills, in this case, trigonometry, to be able to get theta 1, theta 2, and theta 3. So I have calculated those here. Theta 1, based on the lengths that we have here, opposites and opposites and adjacent. So for theta 1, I'm using minus 2 as because this is 90 degrees at this point. Here, at this point is 90 degrees. So you have 2 divisions and you have another 3 up there. So you can have theta 1 being 56.3 degrees. You can also calculate for theta 2, you'll get 71.6 degrees. Theta 3 is the angle here, which because it's minus 2, then that angle is simply the right angle. So it's 90 degrees. And then theta 4 is 108 degrees. Remember, all angles must be measured from the real axis in a counterclockwise manner. Okay, so if we look at these points, so let me remove the homework that I gave you first. So if we look at these points and we try and check, if you sum up all the angles sum up to minus 70.5 degrees. Remember, the negatives are very, very important. Now, we said that the condition should be that the angle condition is that we must have 180 degrees or an odd multiple of 180 degrees. What we were summarizing as 2K plus 1 into 180 degrees, meaning K can be 0, plus or minus 1, plus or minus 2, and so on. So that K ensures that it is an odd multiple of 180 degrees, with the smallest angle being 180. And remember, it can be plus or minus. So here, in this case, the angle is minus 70.5 degrees. Clearly, that is not anywhere near being 180 degrees or even an odd multiple of 180 degrees. That therefore means that you qualify the point and say, therefore, or I could say, let me say, since, because that's how I expect you to solve this question. Since you can say, since the angle of the test point is minus 70.5 degrees, it does not meet the angle condition. Therefore, so if it does not meet the angle condition, therefore the test point does not lie on the root locus. And you leave it at that point. Because once the point is proven not to lie on the root locus, there's no need to get the gain or to do the magnitude condition. There's no need. It's already failed. Okay? So that is very important. That is why I had asked you to try another test point using the same poles and zeros. If we moved the test point, so now that if the test point, so again, this is to check on your, for those who did the homework, if the test point is, what was the test point? It was, let me just check again the question. The test point was given as -2 plus or minus, not plus or minus, plus j root 2 over 2. Okay? So now that's the new test point. Meaning what we have now, it's the same point. It's the same point, but now this is root 2 over 2. So this point here has changed. This point here has changed. Now we have root 2 over 2. This point is root 2 over 2. So you do exactly the same test to find that if the angles that all these poles and zeros subtend to the new test point, and we see if it will add up to 180. So if you check that point, clearly, I cannot keep referring to this, but I know you now know what I mean. We can check for theta 1, theta 2, theta 3, and theta 4. So what is theta 1? Because we are now having the opposite length is now root 2 over 2. The adjacent remains the same. So we are going to have theta 1 to be equal to theta 1, which now is going to be equal to the inverse tangent of root 2, because that's the opposite, over adjacent, which is 2 units. You can solve this. I think you should find 19.5 degrees. I'm only doing this for you because I didn't do it in the previous class, and time is of the essence because I have a lot to cover today. So if I do theta 2 is this one here. So again, that is the opposite is root 2 over 2. The adjacent is just 1 unit. So we are going to have the inverse tangent of root 2 over 2, and the opposite, the adjacent is 1 unit. So you should get 35.3 degrees. And then theta 3, as usual, you can see, because it's directly perpendicular to the test point, it is 90 degrees. So theta 3, by virtue of its location, is simply 90 degrees. All angles measured counterclockwise from the real axis. And then lastly, theta 4 is, and remember angles, you have to write that they're degrees. Don't just leave the angles as numbers. I will not take that. So theta 4, because we are looking at this angle from the, notice from the real axis, but our trigonometry can help us find this small angle here, then we subtract from 180. So theta 4 would be 180 degrees minus the inverse tangent of root 2 over 2. That's the opposite. The adjacent is 1 unit. And then you'll have 144.7 degrees. Okay? So therefore, if you add theta 1 plus theta 2 plus theta 3 plus theta 4, I should get 180 degrees. That is what the rule is. However, remember, when I say you add, if the angles are for poles, so for poles, we subtract the angles. Because they're in the denominator, we subtract angles. But for zeros, we add. Okay? So like theta 1, for example, theta 1 and theta 2 are zeros. So we add them. So we have our angles here. Theta 1 is 19.5. Theta 2 is 35.3 degrees. Now, we are supposed to add theta 3, but theta 3 is a is a pole. Theta 3 is a pole. You can see that theta 3 here is subtended for a pole, and theta 4 is also a pole. So those two are subtracted. That's the condition. So theta 3 is subtracted, and theta 3 is what? Theta 3 is 90 degrees. And then we also subtract the other theta 4, which is 144.7 degrees. So if you subtract all these angles, I think you should get something, because this is negative already, this is negative. So the answer is going to be about negative 180 degrees, which meets the angle condition, because the angle can be negative or positive as long as it's it's 180 degrees or an odd multiple of 180 degrees. So because this point, the test point, therefore, the test point minus 2 plus j root 2 over 2 lies on the root locus, because it meets the angle condition. Now, because it meets the angle condition, we must complete the test by doing the magnitude. But for the magnitude, we want to know what is the gain at where this point lies on the root locus. What is the gain? And remember, the magnitude condition, as was given to you, is here. For those who have forgotten, the magnitude condition is this. Is this. That was the magnitude condition. And we did mathematical manipulations to find that. It's like saying K equals to 1 over G of S, H of S, okay? So that is the magnitude condition. We made K the subject of the formula. Now, ladies and gentlemen, if you look at our feedback system, you can see that H of S is 1 because it's a unity feedback system. So G of S is our feed forward transfer function. So therefore, you can see from our equation here that H of S is 1. So it's just like saying 1 over the magnitude of G of S. This is sometimes referred to as 1 over M, so that you substitute the denominator with we use just a symbol, a letter to represent it, okay? Now, what we can do, what has been done before, I've told you this, that K, which is now 1 over M, is given, if you want to obtain it, you get the product of the pole lengths, not zero lengths. Remember, it's the product of the pole lengths divided by the product of the zero lengths. Meaning, you take all the lengths of the poles, you divide by all the lengths of the zeros, the product of all the lengths of the zeros. The lengths are these lines here. So like I could say, this is L1, okay? This is L2, this other one for the second zero, then this is L3, and this is L4. So what that therefore means is we are having the product of the poles. The poles are L3, let me see again, poles are L3 and L4, zeros are L1 and L2. So that our gain therefore is determined mathematically as, our gain is determined mathematically as K equals to L3, the product of L3 and L4, because the product of the pole lengths, divide by the product of the zero lengths. Zero lengths are L1 and L2. Now, the pole lengths, so we can determine each one of them. So L1 is given by, again, this is getting the magnitude. You want L1. So it's going to be the length squared over height squared, then you get the square root. So this is 2 units and root 2 over 2. So it's going to be the magnitude of root 2 over 2 squared plus 2 squared. I think this should give you 2.12. L2 is the same thing, root 2 over 2 squared, but you have only 1 unit on the adjacent, so you have 1.22. L3, we are just getting this length here. Mathematical methods of, in fact, L3 is simple. It's just this length, and this length is root 2 over 2. So L3 is just root 2 over 2. Root 2 over 2. And L4 is, again, 1.22. So applying K, so K would be equal to root 2 over 2 multiplied by 1.22. That is L3, L4 over L1, L2. So L1, L2 would be 2.12 multiplied by 1.22. And you should find there mathematically, if you calculate that, you should find 0.33. So what we are saying, so this is how you conclude the point. Therefore, the point minus 2 plus j root 2 over 2, okay, this point here is a point on the root locus. It is a point on the root locus for a gain of k equals to 0.33. That is it. So that qualifies the angle and the magnitude condition. That this point now is on the root locus, and the gain at that point is 0.33. So that's very, very important. So you must always consider the angle condition, because that is what determines whether the point is on the root locus or not. And once you realize that the point is on the root locus, then now you can obtain the gain k by using the magnitude condition. The gain k would be obtained, and the gain is obtained using the lengths of the poles and zeros. So it's the product of the pole lengths divided by the product of the zero lengths. Please remember that. Good. So unless there's any question at that point, let me do one last example before I move on to my point today. Again, I hope you're following. Some of these solutions are not in your notes, so I encourage you that whenever I do worked out examples here, you also do them and have those notes. Now, let me do another example. Because usually towards the end of the semester, or when we are about to do our CAT, students ask me for worked out examples, possible solutions, and now here I am doing them. You're supposed to take notes so that you don't ask me for these solutions later. So again, a typical question would be something like this. Given a unity feedback system, that has the feed forward transfer function, that has a that has a feed forward transfer function given by, let's say, g of s equals to k into s plus 2 divided by s squared plus 4s plus 13. Part A, calculate the angle of g of s at the point minus 3 plus j0, okay? Part B, question, determine if the point specified in A is on the root locus. And lastly, if the point in A is on the root locus, find the gain K. Almost similar question to what we have just done. So it should be a very quick solution. So again, remember we are given the feed forward transfer function, which is the G of S. We are to determine there's a test point provided, and in our case, the test point is of course -3 plus J0. So that's our test point. And we are to determine whether the point lies on the root locus. And again, if it lies on the root locus, we need to determine if we need to determine the gain. So the first thing is to find the algebraic sum of angles of all the vectors drawn from zeros and poles that we have here to this test point. Because those angles, if they sum up to 180 or any odd multiple of 180, then we now can start making conclusions. So the best thing usually I told you is to have a diagram or an S-plane that sort of give you an idea of what is expected in your drawing. So you have something like that. Remember, you label your axis properly, okay? So if you check, we have 1, 0, and because this is a second order equation, then we have 2 poles. Now you can check that these poles, you can always calculate this. I think you guys have calculators, can find the roots of this. And so if you get the roots of this, let me see. Somebody tell me the roots of s squared plus 4s plus 13 equals to 0. What's the root? Because I know I can do the 0. The pole is the one I don't know. This is -1, -2, -3, -4. I know that the 0 is at -2, so I have to draw a 0 at -2. I also know that the test point is -3 plus J0. So this is a test point. Notice I just put it as a dot. So that's going to be our test point, -3 plus J0. So I can actually indicate that this is a test point. This one here, this point here is just a test point that we are going to use. That is our test point. So I need to know those 2 poles, where those 2 poles lie. There's the s squared plus 4s plus 13. That tells me it should be somewhere -2. These are complex conjugates. So those poles are going to be, I just need the J part, okay? I don't have a calculator. I just need the J part, but they're going to be, because this is 4, it's going to be -2 plus something and -2 minus something. Anyone to tell me the roots, please? What are the roots? Like what? This is the same as saying K into S plus 2 over S plus 2 minus something, which I want, and then S plus 2 plus something, which I want. So what is this? Is it? Anyone, please? 3, okay. So it's 3I, okay? Or J, whichever you want to use. So let me just use 3J. And this is S plus 2 plus 3J. Okay. So that therefore means that this point should be 3J. Okay, sorry. I like writing as J3. J3. And this point is minus J3. So these are complex conjugates. So it lies on -2, because if you say S plus 2 plus 3J or plus J3, if you make S the subject of the formula, you're going to have S is equals to -2 minus J3. So you'll have a point -2 minus J3 as a pole. and minus 2 plus J3 as a pole. So notice these poles don't lie on the real axis. The poles are on the imaginary axis. It is only the 0 that is lying on the real axis. But the test point also lies on the real axis in our case. Remember, in our solution, we had said that you have to draw a point, you subtend a line from the test point to meet all the poles and all the zeros. Meaning we have to draw a line from here to this. Okay, let me use a different marker. Let me use the red one. Sorry. So we draw from the test point to this, of course, from the test point to this, and from the test point to this. Okay? I think this is a straight line. Okay? Like that. So, and this is the test point. So again, we just need to know the angles. Now remember, and this is very important, that's why I'm trying to do this example with you guys. We want to add or sum algebraically all angles of G of S, meaning all angles of the poles and zeros that they make with the test point. But those angles must be measured from the real axis. So it's like saying, if I drew a real axis on, because this point is on the imaginary axis, the pole. So if I drew a typical line there, let me just even draw a line. There's no point of struggling with dots. Let me just draw. So if that is the real axis, and of course, that is the imaginary axis, we want to know this angle here from the real axis all the way to the point it makes with the test point. So we can call this angle θ1. Notice it is the point measured from the real axis to the test point. Now, we can call this, because I'm trying to do the also for this one, for the conjugate. So again, if we had, because this is, so if we had a point here, okay, like that. So I'm just trying to draw a real axis, a small real, and a real axis within the imaginary line, so that we get to know the angles. So we are referring to the angle from the real axis that it makes with the point, the test point. So we can call this θ2. Notice I'm measuring all my points from the real axis to the test point, counterclockwise direction. And of course, you can see this one is easy, because if I'm measuring again from the real axis to the test point, it's actually 180 degrees. Let me just call it θ3. But you can see it's just 180 degrees, because you're measuring from the real axis. And since the 0 is already on the real axis, we just draw, the angle is measured straight to where the test point is. And so we have θ3. So our test is, if we sum up θ1, we hope that θ1 plus θ2 plus θ3 should give us 180 degrees, or an odd multiple of 180 degrees. Please remember, the zeros are added, the poles are subtracted. Good. So let's see if we can obtain the angles. So let's start with θ1. So what is θ1? θ1 is easy. What we can do is we can get this angle here, because if we get that angle, it should be the same as this angle. This is like an isosceles triangle, because these are complex conjugates. This is spanning 3, this is spanning 3, and they are all meeting at a test point. So you guys know about your isosceles triangles, meaning this angle here is the same as this angle here. So you can get either of those angles, and this angle here is also the same as the angle here. It's the same thing. But we know that this angle is 90. This one is 90 degrees, because the total angle there is 180. So we need to obtain that angle, which again should be very, very easy for you. We can obtain either. Once we obtain one of these angles, because this is an isosceles triangle, we can get all the angles that we want. So for example, if I wanted to obtain, this is 1 unit and this is 3 units. So this angle is going to be, I'm just trying to find this angle here. It's going to be, let me call this angle phi. Okay, phi. So phi is going to be the inverse tangent of 3, because that is the opposite, the adjacent is 1. And that, I think we have calculated before in the previous case, is 71.6 degrees. So if this is 71.6 degrees, then this angle here is 71.6 degrees. And therefore this angle here, the angle inside here, this one here, should be 18.4 degrees. Even this angle here should be 18.4 degrees. That's maths. You should be able to do it yourself. So theta 1, actually, we are looking for 180 plus 71. So theta 1 should be 180 plus 71.6 degrees. And I think that should give you, let me see, it is 256, 250, 251.6 degrees. That is theta 1, just this angle from the real axis all the way to that point. Theta 2 should be 90 because this point is 90 degrees plus 18.4. So it should be 90 degrees plus 18.4. You can use any method you want as long as you get the angles right. I don't have a problem. And this, I think, is now 108.4 degrees. And theta 3, of course, you can see is 180 degrees because it lies on the same real axis as the test point. The 0 here lies on the same axis as the test point. But the rule is the pole angles are subtracted. The 0 angles are added. So let's see. Theta 1 is for a pole, so we have to subtract it, which is minus 251.6 degrees, because it's a pole. All pole angles are subtracted. All 0 angles are added. Theta 2 is also a pole, so minus 108.4 degrees. Theta 3 is for a 0, and 0 is added, so plus 180 degrees. So what do we get when we sum up this? When you sum up this, yes, so you can see that this becomes minus 180 degrees. Minus 180 degrees. So it meets the angle condition. So the question was, calculate the angle of G of S at the point minus 3 plus J, 0. And the angle is minus 180 degrees. To put it into perspective, it means that this test point here makes minus 180 degrees with the real axis, which is true because if this is the real axis and this is your test point, whether we have, and you know we are measuring our angles in a counterclockwise manner from the real axis. So this is 180 and this is minus 180, but that is the same point anyway, because we know 180 degrees and minus 180 degrees is one and the same thing. The only thing is the direction you took was opposite, but it still leads you to the same vector, the same point, I mean. So this proves our point that our test point is 180 degrees from the real axis, whichever direction you take. And so this point lies on the root locus because it meets the angle condition. Okay, so part B was saying determine if the point specified in A is on the root locus. So point B, so this was the answer to solution to point A. Solution to point B, because this is the angle they asked us to calculate. So you say the test point minus 3 plus J0 lies on the root locus because it meets, since it meets the angle condition. And in our case, the angle condition generally is 2K plus 1 into 180 degrees. And ours, in our case, K is 0. K is 0, so that the angle itself is 180 degrees. Because 180, remember the angle condition should be plus or minus. So the angle could be 180 degrees or minus 180 degrees. It's the same thing. Now, but C, because it meets the angle condition, we can now obtain the gain K, capital K. Remember, this is small k. This one is small k. So the capital K, I told you what we refer to, some books will call it 1 over m, is the product of the pole lengths over the product of the zero lengths. Okay? So now you come here and give them, you provide the lengths. So you can say this is L1, this is L2, and this is L3. The length from the pole to the test point, the length from the zero to the test point, the length from the other pole to the test point. Those are the lengths we are talking about. So the pole lengths in our case would be L1, L2 divided by L3. And L1, again, maths will tell you L1 is 3 squared plus 1 squared square root. Okay? So L1 is 3 squared plus 1 squared square root. That is root 10. L2 is the same thing because that's an isosceles triangle. So again, you get root 10. And L3 is simply the length from the test point to the zero, which is just 1 unit. So that's just 1. Therefore, if you have your L1, L2, then you have root 10 multiplied by root 10 over 1, and your solution becomes 10. Okay? So it means that the test point minus 3 plus J0 lies on the root locus, and the gain at that point is 10, meaning the value of K, this is the test point, the value of K here, K is equals to 10. Okay? Maybe if you obtain, when K is 100, you might find that now it lies on this side. But when K is 10, notice it's on the left half plane. So our system is stable. Okay? So that marks the end of the third, because the third question was asking for the gain. So that is how you obtain or you test whether a point is on the root locus or not. And you're also able to tell its, gain at that point, right? Good. So now you've noticed that what I have done with you guys so far is simply take, you're given a feed forward transfer function, and then you are able to test a point. You're given a point to test whether it lies on the root locus or not. But we have not drawn or even sketched any root locus yet. And so now that is what we want us to move on to. So sketching root locus. Sketching root locus. Because now we need to draw or at least sketch this root locus so we see what we have been referring to. What we have done so far is simply to know whether a point lies on the root locus or not, and to know the gain at that point. But we have not actually sketched the root locus. Now, there's a reason why we are using the word sketching. You see, from the previous discussion we've had, the root locus can be obtained by just sweeping through every point on the S-plane. You simply check all points on the S-plane and you locate those points that meet the angle condition and also the magnitude condition. But that task can be tedious because you can imagine if this is an S-plane. So I've given you points like that. All these are points. Are we going to test each point one at a time, both for the angle and magnitude condition? Because we need to know whether it lies on the root locus and we need to know its corresponding gain. So you can imagine you being given 1,000 points on the S-plane and you're supposed to test whether they meet the root, the angle and magnitude condition. It is a very tedious process. So manually, it's a very, very tedious process. But with computers, it's a very, very easy. The concept can be done very easily with the aid of a computer. But if you don't have a computer, like in this case where we are actually studying, we cannot be able to test for all points. If it takes us about 10 or 15 minutes to test for only one point. If we had 1,000 points, we'll take forever. So we have certain concepts that can be used to develop rules that we can use to sketch the root locus without the effort of testing, for the angle and magnitude conditions. And those rules are very important because they help us to sketch. So it is not an exact root locus because the exact root locus can only be obtained with the aid of a computer. And I'll give you examples of those. Even in your notes, I'll put some codes. You will see some codes that you can type into MATLAB, and it will give you the root locus, or it will help you obtain the gain, or it will help you obtain the angles and all that. You can always just type a code and it gives you the answer. But you see, in an exam setting, you don't use computers. You have to do it manually. And if you're an engineer, your design should first be done manually before you develop computer aid programs, okay? So we need to be able to obtain a sketch using certain rules, because once we have a sketch of the root locus, it is possible for us to accurately plot just those points of interest. For example, you see, if I was to test all these dots that I've given here, it would take me forever. But if, for example, if our sketch of the root locus appears like that, then it means it is only this point that will be considered, and only this one, and only this one, and only this, and maybe this. The rest are out of the root locus, so they are not points of interest at all. That is why root locus is important, the sketch, because the sketch will actually give us a sort of like an accurate plot of just the points that are of interest for any particular problem. So if our plot was like given, you can see that we can narrow down to only 5 points rather than the 1,000 points that lie on our S-plane. Okay, that's the essence of sketching the root locus. It saves us a lot of time. Okay, so we have rules that allow us to sketch the root locus using very minimal calculations, because we still have to do a few calculations, but they will be very easy calculations. And these rules yield a sketch that gives you a very intuitive insight into the behavior of a control system. When I talk about the behavior of a control system, is you're able to know certain characteristics of the transient response, you're able to know certain characteristics of the steady state response, and you're able to know its stability conditions. Okay? So the first rule is referred to as the number of branches. Number of branches. Remember, at this stage, we are only sketching. So I'm going to do very, very basic sketches. So please pay attention, because this is where you develop the skills to plot root locus. I can already tell you, your CAT is going to have sketching root locus. Your exam is going to have sketching root locus. You will not escape it. So what does this mean? The rule simply says here, you'll get more notes on the rule so you can read through, but the rule says that the number of branches equals the number of closed loop poles. Number of branches equals number of closed loop poles. Not open loop, closed loop poles. Not open loop, ladies and gentlemen. Let me give you an example, because you'll be confused here for no reason. This is a feed-forward transfer function. If we were to put it on a plot, it would be here. Let me actually give just a quick example so that you don't confuse this point. So mostly you'll be given a transfer function there. Maybe we are using a unity feedback system like that. So this is G of S. So C of S over R of S is given by 1 over G of S, H of S. Okay? Here K is 1 maybe. So if we had 1 over 1 plus, is it 1 over 1 plus G of S, H of S, yeah? Meaning we are getting the closed loop transfer function. So if you get the closed loop transfer function, then the poles of your closed loop transfer function are the ones that are equal to the number of branches. Okay? So remember, when we are plotting the root locus, we actually just use G of S. But if you want to know the number of branches, like how many branches are there in your root locus? When I say how many branches, I mean the root locus, this could be one branch, and then it branches another branch, and then it branches another branch, you know? So like you can see that how many directions does it take? That is the branches, okay? So the branch is a path that a pole traverses. That is a branch. So if a pole, please mute your microphones. If a pole begins from the origin like that, if it traverses or it moves in that direction, then that is a branch. If again it branches to go upwards, that is a branch. If another one branches to go downwards, that is a branch. It is the path that one pole traverses. That is called a branch. So if you want to know the total number of branches in your root locus, then you have to obtain the closed loop poles, meaning get the closed loop transfer function, and then you get the poles. But I'll give you, we'll draw a lot of this, so it will be very, very easy to relate with, okay? That is rule number 1. Rule number 2, I'll try and give an example as we go along. Let me just give the rules first. The rule number 2 is on symmetry. Because remember, we are using certain skills or rules that are going to help us to quickly draw a root locus without having to do tedious mathematical computations. Now, the rule on symmetry is that the roots of the characteristic equation can either be real, they can be complex, or it can be both real and complex. Okay? Meaning if you obtained C of S over R of S, you know you'll have something like 1 over 1 plus G of S, H of S. You know, if there was K, then you'll have K there. So if you get this, of course, becomes your characteristic equation. If you get the roots, sometimes the roots can just be real values, or they can be complex values, or they can be a combination of both real and complex values, okay? But the rule is, even if they're real or complex or whatever, the root locus, the rule is that the root locus is symmetrical. This is very important. When you're drawing your root locus, please note it is symmetrical about the real axis. Very important. This is what we mean. We are always going to use an S-plane. And whenever we use an S-plane, we are going to draw a root locus. But you will notice that despite the number of poles and zeros that we have on our root locus, you will always notice that the root locus is symmetrical. There's some level of symmetry such that you'll find that, for example, if a pole is moving in that direction, the other one is also moving in the opposite direction. Or if they're moving through the imaginary axis, so one is moving like that, the other one probably is moving like that. You see, so there's some level of symmetry that we obtain about the real axis whenever we draw our root locus. So it is never asymmetrical, it is symmetrical. So if you find that you're drawing or sketching a root locus and there's no symmetry, then you have a problem, because there's always symmetry of the root locus around or about the real axis. We'll draw a couple of those root locus or root loci, and you will see that that symmetry applies. The other one is on real axis segments. Now, on the real axis segments, the rule here is that on the real axis, for values of gain that are greater than 0, okay? For gains that are greater than 0. Please always remember that whenever, this is just a side note so that I don't forget later, where a root locus begins, even if it begins here, where a root locus begins, the gain is considered 0. Remember, we said that root locus is a plot or a graphical illustration of the path or trajectory of poles as the gain moves from 0 to infinity. Okay? So, as the gain moves from 0 to infinity. So, at the end of the day, it means that where the pole begins its journey, the gain at that point is considered to be 0. So on the real axis, okay, we are saying that for a gain that is greater than 0, the root locus exists to the left of an odd number of real axes. Let me just write it fast, then I explain. The root locus, I'll denote root locus with RL so that I don't keep writing that. The root locus exists to the left of an odd number. Please remember this, ladies and gentlemen, of real axis, not imaginary axis, of real axis and finite open loop poles. This is very important, so I'll have to explain each point. Or finite open loop zeros. This is probably one of the most important rules of the root locus sketching. This is one of the most important ones. And I think I need to simplify it, at least to explain it further. Now remember, let me explain it by drawing an S-plane. And you have G of S equals to S plus 1, S plus 2, S plus 3. Now, please pay attention here, ladies and gentlemen. There's so many points that I've talked about here. One, on the real axis, meaning this rule, that's why it's called real axis segments. This rule only applies on the real axis. It does not apply on the imaginary axis. It only applies on this horizontal line. This rule only applies on this horizontal line. But you will notice that most root locus begin from the real axis. Then they decide to branch out to the imaginary axis. Certain times they can begin from the imaginary axis, but most times they begin from the real axis, they branch out to the imaginary axis, and then they come back to the real axis, or they go to infinity. So this rule only applies on the real axis. And it is saying, so notice this, here you can see there's a 0 at -1. Let me say that's -1. There's a pole at -2. So this is -2. There's another pole at -3. Let me even add another one, S. So there's a pole at 0, okay, the origin. There's another pole at -3, like that. So notice I've just plotted. Remember, this is the open loop. Okay, poles and zeros. If I were to get the closed loop poles and zeros, it would be 1 over 1 plus G of S, H of S. Okay, then I would get the roots of the characteristic equation. But these are open loop poles and zeros. So please note, whenever you're plotting the root locus, whenever you're sketching the root locus, we are using the open loop poles and zeros, aka we are using the feed forward transfer function. We are using the feed forward transfer function. But if I want to know the number of branches in my root locus, I have to get the closed loop transfer function so that I get the roots of the characteristic equation, and that would become the closed loop poles. And those poles, if there are 4, then I know I have 4 branches on my root locus. But when you're sketching, when you're just sketching a root locus, you use the open loop or the feed forward transfer function. So look at this, ladies and gentlemen. This was my point. I say that the real axis segment rule only applies on the real axis, meaning if you can look at the number of zeros, I have only 1 0. In my transfer function, I have only 1 0 and I have 3 poles. The rule says that a root locus exists to the left of an odd number of real axis, finite, open loop poles or zeros. So let me define each one of them before we now look at what the rule says. It must be real axis, meaning the poles and zeros must lie on the real axis. Number 2, they must be finite. Finite means we must actually locate them. If they are infinite, then we can't plot them on the root locus because we can't obtain an infinite point on our S-plane. So those poles must actually fall on the root locus. They are values that we can obtain their location on the S-plane. Because infinite means we cannot obtain their values on the S-plane. So we cannot actually plot them here. But for those that we can plot, because please note that root locus goes to infinity. Remember K, we had said K goes all the way to infinity. But we can't plot a point at infinity, but we know it exists. So there are certain ways in which we represent those, and I'll show you later. But for now, we just want to note that as long as the points are finite, if their values are 1, 2, 3, 4, 5, 6, 7, 10, you can put them on the S-plane. They must also be open loop, meaning we've obtained them from the feed-forward transfer function. And they can be zeros or poles. So the rule says that a root locus exists only on the left of an odd number of real axis. Now pay attention to what that means. It means if I wanted to plot the root locus here, there is a hint of how or where the root locus lies. The hint is this. You begin, because you notice it says the root locus exists to the left. So if you want to obtain this rule, you must go to the rightmost pole or zero. In our case, the rightmost pole or zero is the one that lies on is at the origin. Even if it was here, then we would begin from here because we are considering everything to the left. So in our case, the rightmost, it's a pole in this case, but it is a pole and it is at the origin. So the root locus, if I want to know on the real axis, where does the root locus lie on the real axis? It is always to the left of an odd number of either a pole or a zero. So you come and say, this is the first pole. It's either a pole or a zero. So in our case, it's a pole. So because it is pole number 1, so this could be pole number 1. This is a 0, but it is number 2. This is a pole, but it is number 3. This is a pole, but it is number 4. So we are not saying this is the first 0. No. We are considering both poles and zeros. As long as they lie on the real axis, we give them numbers 1, 2, 3, 4 in our case. So you look at the rightmost, which is this one, and we see that being number 1, 1 is an odd number. So since 1 is an odd number, it means that the root locus lies to the left of that odd number pole. Then you come to the second one, which is now a 0. But this 0 is number 2. 2 is an even number. So it means to the left of an even number, whether it's a pole or a 0, there is no root locus. Then you come to the one at -2. It is a pole, yes. Even if it was a 0, it doesn't matter, as long as it's an odd number. So in this case, it's number 3. Because it's an odd number, to its left, we must have a root locus. That's why I'm drawing it in red. Then we go to the next one, which is at -3. It's a pole, but its number is 4. So because 4 is an even number, root locus cannot lie on the left, which means on the real axis, the root locus will go to the imaginary axis. But in order to sketch, the first hint is that the root locus lies at between these two and between these two. Why? Because it has to be on the left or to the left of an odd number of either a pole or a zero. So this is number one, to the left, there's a root locus. This is number two, to the left, there's no root locus because this is an even number. To the left, number three, then there's a root locus. To the left, number four, because four is even, there's no root locus. Okay? That's very important. That's what we mean. I don't want to draw the root locus at this point. I'll come back and draw the root locus. But we know that, of course, on the real axis, those are the root locus points. But it's not complete. I'll come and complete it later because we still have other rules that I must put in place. Then we will draw that, okay? So now let's go to number four, rule number four. Today, at least, I needed us to draw a root locus before we go. Number four is starting and ending points of the root locus. Notice these are just rules that help us sketch a root locus without having to do mathematical manipulations. Starting and ending root locus. So that means, where does the root locus begin and where does it end? So the rule is that the root locus begins at the finite and even infinite poles of G of S, H of S. So if H of S is 1, then it's just G of S, and ends at the finite and infinite zeros of G of S, H of S. In case of a unity feedback system, H of S is 1. So we're just talking about G of S. Remember, this is very important. Let me just write here. Remember that these poles and zeros are the open loop, not closed loop. They are the open loop zeros. Open loop poles and zeros. These poles and zeros are the open loop poles and zeros. So on the right are the open loop poles and zeros. Meaning you obtain them from G of S. Okay? That's what it means. You don't obtain them from C of S over R of S, which is 1 over 1 plus K G of S, H of S. No. You only use this formula whenever you are trying to see how many branches do I have, and so on and so forth. But when you're just sketching the root locus, we use G of S. Okay? So in this case, let's go back. What this means, rule number 4. Where does a root locus begin and where does it end? It says that a root locus can either begin from, in fact, it begins from a finite or infinite pole and ends at a finite or infinite zero. Meaning, a root locus will always begin from a pole, whether that pole is finite or infinite. It must begin from a pole and it must terminate or end at a zero. So again, let me apply that rule to what we were drawing here because we didn't complete the root locus. So we are trying to plot the root locus of this point, but I'm just using the rules as we go along. So the root locus must begin from a pole and terminate at a zero. So we have established from rule number 3 that the root locus lies between this odd number or to the left of an odd number of pole or zero. So we know there's a root locus here, but in which direction? Is it to the right or to the left? I look at this as a pole and the other one as a zero. So the root locus must begin from the pole and go towards a zero. That's what it means. So if I was to draw, because you have to draw the direction of the movement. So it must begin from a pole towards a 0. So even for these two, they must begin from a pole. So it must begin from a pole. Even for this other pole, it must begin from a pole. So you see, a root locus must begin from -3 towards a 0, and that 0, we don't know where it is at this point. The one at -2 must also begin from there towards a 0, meaning a root locus must begin from a pole, but it must also find a 0 so that it completes its journey. Once it begins from a pole, it must end at a 0. Now, that 0 can either be in a finite location or an infinite location. So come to this diagram again. You can see that the first root locus point that we drew here, there's already a pole where the root locus begins, and there's a 0 next to it where the root locus ends. So the pole is finite, the 0 is also finite. You see that? That is complete. When you come to the one between, because the root locus lies between point -2 and -3, both are poles, because there's a pole at -2 and there's a pole at -3. The root locus must begin from a pole, meaning it must begin from -2. But because -3 is also a pole, the root locus must also begin from a pole. So they are moving away from the pole, because it must begin from a pole. Their destination is always a 0. It is at a 0 that the root locus terminates, okay? But in our case here, in our G of S, there is only one 0 provided. But we have 3 poles. Notice we have the pole at 0, at -2, and at -3. It therefore means if a pole must terminate at a 0, then it means that we have zeros here. There must be 3 zeros. Because we have 3 poles, we must have 3 zeros. The only difference is the 3 poles that we have are finite. But we only have one finite 0. Only one 0 that we can see on the S-plane. The other zeros are infinite. That's why they're not plotted here. They are infinite. That's what we mean. Because we have 3 poles, each of them must find a 0 to terminate at. Okay? But we only have one that is finite in nature. The rest are infinite. So therefore, it means that at some point, these 2 poles must terminate at a 0. Those zeros are at an infinite location. So how do we know where the location of these infinite zeros are? We will come back to that later, using another rule to tell us how then do we plot the root locus from this point, because we must terminate. At least for the one at the origin is terminated at -1, because at -1 there was a 0. That's very convenient. So it terminates there nicely. It's like this pole here has found the girlfriend, so they are fine. But now these 2 guys here are on their own. We must find them girlfriends. But where are they? So we must look for a rule that will tell us where those girlfriends are. So how do we do that? We will use another rule. But I wanted us to understand the starting and ending point of a root locus. The root locus must always begin at a pole and terminate at a 0. Whenever you draw a root locus, ladies and gentlemen, you must draw the direction. The direction is what shows us where the root locus begins and where it terminates. Okay? I hope that point is clear. Okay? Now, I want to demonstrate this starting and ending in another using another example to just give you a better illustration. We'll come back and complete this because there's other conditions that must be applied there. So for example, let me sketch, let me say this is already provided. Let me just, because I need us to draw root locus today, but we need to understand the rules first for sketching. So let's assume we have a pole at -1. We have another pole at -2. We have a 0 at -3. And we have a 0 at -4. And again, please note, ladies and gentlemen, Sometimes I will give you G of S. Sometimes I will plot the route, the poles location. So you have to tell me what G of S is. Okay? Meaning, this is the S plane. If I just give you a diagram like this, you will definitely know that G of S should be equal to, because these are zeros and these are poles, you should just tell me the G of S should be S plus 3, S plus 4 over S plus 1, S plus 2. So sometimes I'll give you this and I expect you to be able to come up with the plot, or sometimes I give you the plot and I expect you to know what G of S is from there, and you can be able to do manipulations. So from the rules that I gave you again, let's try and apply the rules. We said we first need to know where the root locus lies on the real axis. How do we know where the root locus lies on the real axis? We begin from the rightmost pole or 0. So this is the rightmost. And because it is the first one, root locus must be on to its left, because number 1 is an odd number. Okay? This is the second one. So that's an even number. So to its left, there's no root locus. This is the third one. Because it's number 3, to its left, there's got to be a root locus. This is the fourth one. And because it is an even number, then to its left, there's no root locus. So on the real axis, the root locus lies only on these points. But rule number 4 says that a root locus must begin from a pole and terminate or end at a 0. If you look at our G of S, we have 2 finite poles and we have 2 finite zeros, meaning it's an even match. The poles will, each of these poles will find a 0 to terminate at. But which one will terminate where? That's the point. Now, remember the directions that I told you about. Because this is a pole, the root locus must leave the pole towards a 0. We don't know which 0. Because the second one is also a pole, the root locus must leave that pole, but we don't know to what 0. Because the third one is a 0, the root locus must terminate. So notice it is entering the 0. And because number 4, at -4, we also have a 0, the root locus must terminate or end. Sorry, what did I do? It must end at that 0. So you can already see the direction. And remember, the root locus is the plot or the trajectory of the poles as gain increases from 0 to infinity. So what happens in this case? It means that the pole between -1 and -2 will start their journey to terminate at a 0. They will meet somewhere in the middle. We don't know where. We'll calculate that point later. But they'll meet somewhere in the middle and realize that because we are both poles, we cannot terminate at each other. We must look for zeros to terminate at. So at this point, it's sort of like there's a force coming from the left and there's a force coming from the right. They cannot stay on the real axis here because they are looking for a point to terminate, which must be a 0. So what happens is, because number 2, pole 2 is pushing and pole 1 is pushing, they will split, or what we say, they will break away. That's the word. They'll break away. And when they break away, they'll break away into the imaginary axis. So the direction would still be upwards and this one will go downwards, because they are poles. They are like, they don't agree. They'll repel. It's like poles repel. So they'll repel each other. They'll break away in search for zeros to terminate. So this guy will terminate. One of them will go upwards. The other one will go downwards. For us, we cannot know which one will go up and which one will go down. But if you plot it in MATLAB, it will use the same color. So you will know where number 2 will go, where number 1 will go. But for us, we'll know that they'll still move to the imaginary axis. But we don't know which one will go down and which one will go up. Now remember, they are looking for these 2 finite zeros so that they terminate. So it means one will move and then they'll realize that the zeros are at the real axis. So they'll come back, it will come back there and terminate at one of them. And this one will also move. Remember, I told you there is a symmetry. That was rule number 3. Is it rule number, no, rule number 2, symmetry. So If this one is moving upwards in that direction, the other one is moving downwards in this direction. Okay, until they terminate. So notice the the direction. So there is some symmetry about the real axis. So notice where they began. One began at -1, another one began at -2. They realized that they are both poles, but they must terminate at zeros. They cannot terminate at each other. Because of the force of each one of them, they break away into the imaginary axis in search of those zeros. Then they realize that zeros are on the real axis. So they come back. And so this point, we look at this again in the next class. This point is always known as the breakaway point, the point at which the poles leave the real axis into the imaginary axis. And it's a very important point that we must calculate. We'll do that later. Then here is the point where they break in. So this is known as a break-in point, the point at which the poles rejoin the real axis from the imaginary axis. Is known as the break-in point. So you are always asked to calculate both those points. It's easy to calculate because once you calculate, you know that the answer for a breakaway point must be between -1 and -2. So it has to be somewhere there. And the point of the break-in in this case must be between -3 and -4. So if your solution is smaller or greater than this range, then you know your answer is wrong, because the break-in must be between point -3 and -4. So it must be -3 point something, and the breakaway point must be -1 point something. That's very obvious from the observation there. So this is basically a root locus now. Whatever I've drawn in red is a root locus. And notice it gives the direction of movement. Now, when you plot this in MATLAB, it would even be more clearer, because what it will do is it will give you the path of each pole on its own color. So it will give you a color code for maybe the pole at -1. It will give you the direction using that color. So you will know exactly the direction followed by that pole from -1 up to the point it terminates. But when you observe it manually, we cannot tell whether it is -1 is the one that terminates at -3 or it's the one that terminates at -4. But the MATLAB will tell you which zero each of these poles terminates at, okay? But that's not important at this point. What is important is you're able to sketch the direction of the pole as it originates from its pole and terminates at its zero. Please remember, the point at which this pole leaves here, the gain is 0. The point at which it terminates, the gain is infinity. I hope that's very clear. So it means the gain here is K. If you increase the gain, it moves. You increase the gain, it moves. You increase the gain, it moves. So gain is 5, 10, 15, 20, 25, 30. It will just be moving like that. And the gain increases. By the time it terminates, the gain is infinity. The same thing for this guy. When it begins here, the gain K is 0. The gain is 0. You increase the gain to 10, it moves. To 50, it moves. To 100, it moves. To whatever value, 10,000, it moves. It moves. By the time it moves in the other direction. I don't know which one moves in what direction. By the time the gain gets to infinity, it's terminated at the 0. That's why we define the root locus as the graphical illustration of the trajectory of poles as the gain increases from 0 to infinity. Meaning at the origin, where the pole originates, the gain is 0. At the end, where the pole terminates or ends, the gain is infinite. I hope that is very, very clear. I've spent a lot of time trying to explain that point. So allow me to use the last rule, rule number 5, because there are first 5 basic rules. And then we plot a couple of the root locuses, or root loci for that matter. So number 5 is, remember I have mentioned infinity. So the behavior at infinity is the last rule here. Behavior at infinity. Forget about breakaway and break-in points. Those ones will be used in the next class as we refine. There's something called refining the root locus. I'll give you notes so you can read ahead of me. But let's look at the behavior at infinity. How do the poles and zeros behave at infinity? Okay. Now, because we are sketching the root locus, ladies and gentlemen, it is very, very difficult for us to sketch points that lie at infinity. For example, in this case, both the poles and the zeros were finite. So it was easy to sketch because all those points lie within our S-plane. In the previous case, which is this one, we only could terminate one of the poles. We terminated the pole at the origin, we gave it its zero, so it terminated. Here the gain was zero, here the gain was infinite, okay? However, for these two other poles, we have now established that because they repel each other, they'll get to a point where they break away into the the imaginary axis, as each one of them is attempting to look for the zeros at infinity. But how do we determine where those zeros at infinity are so that we are able to plot the direction? Because we don't know whether at this point they're supposed to be moving towards that direction, or they're supposed to be moving towards that direction, or even they're just supposed to be moving straight ahead and straight ahead. There's no way of knowing except when we consider the rule of the behavior at infinity. So let's consider that rule, and then we start plotting a couple of them. So consider, we are going back to this. Don't worry, we'll go back to this. What I want us to do now is, and let me just remove that. We'll go back to it because it's a simple example and it's important to illustrate it. So we'll go back to it. But before we do, let's use a general rule for the behavior at infinity, okay? And that's a very important rule that would help us. I have about 30 minutes. Let me see if I can quickly do that. So assume we have an open loop transfer function. Let's have an open loop transfer function here. Ladies and gentlemen, if I do this, you should understand what I mean is, if I remove the k on both sides, so if I divide both sides by k, I'll have g of s, h of s equals to 1 over s into s plus 1, s plus 2. Because I've removed k's on both sides. If it's a unity feedback system, then h of s is 1. So this one is 1. So I simply have 1 over s into s plus 1, s plus 2. So it's the same thing as writing this and this are the same, notice, except if I want to introduce gain and also if I want to introduce the unity feedback system. But it's one and the same thing. But this is the more comprehensive illustration. But anyway, let's carry on. From here, you can see that there are 3 finite poles. There are 3 finite poles. These poles will originate from 0, another one will originate from -1, another one will originate from -2. And they'll want to head towards zeros because for a root locus, the pole must originate at its point where the gain is 0 and terminate at a 0. That 0 can either be finite or infinite. In our case here, there is no finite 0 because, so it means that all the zeros here, all zeros are at infinity. So all the zeros are infinite. Okay? So, and sometimes we can also have infinite poles. Okay? So if the function approaches infinity, like in this case, you can see we have this function here where we have 3 finite poles, but we don't have any zeros. It therefore means that those zeros lie at infinity. Okay? So the only way for us to know the approximate, that's the one I'm looking for, the approximate location of all these zeros at infinity is if we draw a root locus using what we call asymptotes. These are straight lines. Asymptotes are just straight lines, okay, that yes, the straight lines that the poles follow as the root locus approaches infinity. Approaches infinity. Now, remember, those the root locus does not touch the asymptotes, but the asymptotes will give it a general direction of where to follow. Like in this case here, we don't know where to follow. We don't know which direction to take. But if we obtained the asymptotes, then it will give us a general direction of where to draw the root locus. Remember, the root locus will not touch those points, but at least will come as close as possible to those points as we head towards infinity. Because we can only draw a general direction towards infinity. We do not know the exact location because we can't plot an infinite location. So how do we obtain the asymptotes, the straight lines? The asymptotes, you must obtain its angle, okay, and the real axis intercepts. Meaning you have to obtain the real axis intercept and the angle. It's like saying this was your real whatever S-plane, eh? Then you have a point. So we have two poles here, and each one of them must leave the real axis to look for, they must leave the real axis to look for zeros to terminate at. But we do not know in what direction. So we must draw some asymptotes. The asymptotes would be straight lines. So we must know the real axis intercept, meaning the point at which they leave this real axis, and then the general angle of direction. So you might find that it might be, let's say this is 45 degrees. And so the other one, because of symmetry, the other one is also 45 degrees. So that we know that if they leave, they must follow a general direction towards that and this towards this. The asymptote could even be towards that direction, or it could even be 90 degrees, okay, based on your calculation that is given. So how do we draw the asymptotes? This is how we obtain the asymptotes. I'll quickly do that. So the real axis intercept is given by a sigma A because it's the real axis. Remember, sigma was real axis, but the intercept is, so we abbreviate that sigma A. For you to obtain the point at which they leave the real axis, in this case, you have to get the sum, that is the sum of the finite poles. That's why these formulas are very important, minus the sum of the finite zeros. You divide by the number of finite poles, subtract the number of finite zeros, not product, number of finite zeros. That's very, very important. And to obtain the angle, because I told you, you must also obtain the angle. So let's call the angle theta. Okay. So let's obtain the angle theta. Okay. My app has frozen. Something usually has to happen with technology as usual. That is expected. Please bear with me, ladies and gentlemen. I am not going anywhere. I just want to share with you. Let me just look for those notes again. is given by 2k plus 1 pi. Remember, pi is 180 degrees over the number of finite poles minus the number of finite zeros. We are going through this struggle so that we are able to obtain an asymptote or a pair of straight lines that are going to guide us as to the general direction of the root locus towards infinity. K, as usual, remember I told you, was 0, plus or minus 1, plus or minus 2, and so on and so forth. Okay? So that should be very clear. Actually, let me now start. Let me do one example. Then we see how those asymptotes will help us. So, for example, we have a question here. Let me now do a question that will help us plot the root locus. So we plot the root locus for the entire using all the 5 rules. Okay. I've told you these are just lines that are going to help us draw the general direction of the root locus. So let me just quickly do an example before we end our class, because I also need like 5 minutes to give you a brief. Okay, so the question is, sketch the root locus. Remember, it's sketch because you can't draw. You can't draw. It's only a computer that can accurately draw. For us humans, we only sketch. Sketch the root locus for the system. There's a typical system below. Typical question, okay? So in this case, they have drawn the feedback system for us. And this is the system. It's K S plus 3 over S into S plus 1, S plus 2, S plus 4. Notice I take my time to label this. You must do that as well. And it's a unity feedback system. Okay? So you're supposed to sketch the root locus for this. Now, I will start from 5 because 5 is the one that involves calculation. The others don't involve calculation. So let's start from rule number 5. Let's calculate the asymptotes. Okay? So I'm starting from rule number 5 just to illustrate that. So, because the others don't need any calculation, calculate the asymptotes. The other rules are just applied straight away. Okay. The reason why you will see that we'll have to draw asymptotes, ladies and gentlemen, is because you already see that we have 4 poles at the origin, at -1, at -2, and -3. So we have 4 poles, but we only have 1 finite zero. 4 finite poles, 1 finite zero, meaning there are other 3 poles that need to terminate. And it means they'll have to terminate at zeros which are at infinity. Those zeros are at infinity, we must know where they are. And that's why we have to draw the asymptote. I hope that is very clear. That's why I'm saying step number 1, we have to calculate the asymptotes. It assumes that you have already observed your G of S and you've seen that it has 4 finite poles and only 1 finite zero. So there exists other 3 infinite zeros, but we don't know where their location is. The asymptotes will assist us know the general direction of those 3 finite zeros. So let's start by calculating the real axis intercept. The formula is already here. I won't write it. You get the sum of the finite poles and you subtract the sum of the finite zeros. And finite. So here, the finite poles, the summation is the one at 0. We have 1 at -1, we have 1 at -2, and we have 1 at -4. Those are poles. And zeros, you only have 1, the finite one is at -3. So first you have to sum. It says sum of the finite poles. So what are we going to do? We are going to have -1. We are summing up all the poles, -2, -4. Of course, I am not putting the 0. Then you subtract the sum of the finite zeros. we only have 1 0 at -3. Divide by, so notice this is the sum of the finite poles. The second one is the sum of the finite zeros. Divide by the number of finite poles. How many finite poles do we have? 0, -1, -2, -4. There are 4. How many zeros do we have? We have only one finite zero. So if you get your solution here, this is -7 minus -3. That should give you -4/3. Okay? So -4/3, or what we call -1.33, is the point that the lines must leave the real axis. But what is the angle? Theta A is given by, we had said it is 2k plus 1 pi, or 180 for that matter, over 4 minus 1, because we said it is finite poles, the number of finite poles minus finite zeros. So you will see, therefore, that, and remember k is 0. And you can take minus, but in this case, I want to deal with the positive one. So I'll just deal with, because it could be minus or positive or plus. So this is what we must get. So let's say for k is 0, for k is 0, then we substitute this with 0, and we'll have the angle as pi over 3. Because if it is 0, we're going to have pi over 3. For k is 1, then we are going to have 3 pi over 3. For k is 1, we are going to have pi. For k is 2, we are going to have 5 pi over 3. 5 pi over 3, yes. And so on and so forth. You can put as many angles as you want, but they will help you in the plotting. When I say pi over 3, I simply mean 180 degrees, because pi is 180 degrees over 3. So this is like saying 60 degrees. This is like saying 180 degrees. This is like saying 180 by 5 over 3. So I don't know what that is. 180 by 5, I think, should be 900. So I think it should be 300 degrees, something like that. Yeah, 180 by 5, I think, should be 900 or something like that. So now we can now go to our plots. Let me bring you back to our plot. So to plot this, remember the points, the poles are this, and the zeros are that. Okay? So let's try and plot this quickly before we end the class. 5 minutes or less. So we have -1, -2, -3, -4, and so on and so forth. So the first thing is to plot the open loop poles and zeros. So we have a 0 at -3. There's a 0 at -3. So I draw a 0 there. Then we have a pole at 0. Okay. So at 0, we have a pole. We have another pole at -1. We have another pole at -2 and -4. So -2 and also -4. So you have to draw those poles like that. Okay? That was point 0. So at least we've plotted the poles and the zeros, all the finite poles and zeros. We know there exists other zeros at infinity, but we don't know where they are. The asymptote will tell us. So now, look at this. We have to know on the real axis, where does the root locus lie on the real axis? And that begins by saying we look at all the poles and zeros. We number them from the rightmost to the leftmost. So at the rightmost, we have the first one. The first one, because 1 is an odd number, then to the left of the first one, we have a root locus. Okay? Like that. Then the second one is an odd number, so there's not, is even. Number 2 is even, so there's nothing to its left. The third one, because it's an odd number, to its left, there has to be a root locus. So you have to draw like that. Then this is number 4. 4 is an even number, so there's nothing to its left. Then, these things. Then number 5, you can see this is number 5. So to the left, there's got to be a root locus. Now notice I'm putting the arrow in that direction to mean the pole has to, the root locus must leave a pole. So even for this one, the root locus has to leave a pole. But this one, there's a root locus that must terminate at a 0. Again, where the root locus lies here, it must leave the pole. This guy, it must also leave the other pole at -1. So you have to draw the direction. The root locus must leave the pole, but it must end or terminate at a 0. We don't know where. So the one between -2 and -3, you can see is sorted. Why? Because you have a pole where the root locus leaves, okay? Then you quickly have a 0 where it can terminate. So it therefore means that the pole at -2 terminates at the 0 at -3. So this guy here, this one and this one are sorted. The pole at -2 is terminated at the 0 at -3. So what remains is we must determine where the pole at the origin at -1 and -4, where they terminate. Where are their zeros? Their zeros are at infinity, but we don't know exactly where at infinity. Now, this is a very important point. Look at the pole at -4. It is on the real axis. It does not have a corresponding pole. It does not have, a corresponding pole so that they repel each other and move to the imaginary axis. So it is assumed that it is going to terminate at a 0, and that 0 must just be on the real axis, and that is why it moves in that towards that direction, because we are saying that the pole is going to terminate at a 0, which still is on the real axis. The ones that are repelling each other are the ones between 0 and -1. And you can actually see that there's some point where they'll have to leave the real axis to go to the imaginary axis, and then they look for their zeros to terminate at. So we just need to determine the general direction. We already have calculated the real axis intercept as -1.33. So at this point, as at -1.33 is somewhere here. -1.33 is somewhere here. Notice it is not the points at which the poles leave the real axis, but it is the intercept, the point of intercept. Then we will use our skills to try and figure out where the poles go. But remember, this point here we had said is called the breakaway point. The breakaway point is going to be determined in our next class, not here, okay? So please note that the breakaway point is not to be done today, okay? What we are drawing is an intercept, and the intercept has been calculated as point -1.33, which is this point here, -1.33, this point, okay? And we draw a straight line, and those lines can be at 60 degrees, at 180 degrees, and at 300 degrees. So 60 degrees is a straight line like that, and 180 degrees is a straight line on the real axis. So this one, this line here, this intercept of 180 degrees is where the other 0 at infinity, meaning there's a 0 at infinity on this line. There's another 0 at infinity in the direction of 60 degrees. There's another 0 at infinity in the direction of 300 degrees. Because we were looking at where possible, or the general direction of the other zeros at infinity. So the one at 180 degrees is where this one, the pole at -4 will terminate at. That's why it was, the angle here was very important, 180 degrees, meaning the 0 that exists at infinity is at around 180 degrees, and therefore this pole at -4 will terminate there. But there's another 0 at an angle of around 60 degrees. We have drawn that angle, and then the other one at 300. 300 is 60 degrees to the other direction also, so it would be, remember the symmetry that I told you about. Now remember, the asymptotes are not part of the root locus. They are simply straight lines that give us the general direction of the root locus. That is why I'm not drawing it in red, because they are not the root locus. So this is an asymptote. This is an asymptote. They are simply straight lines that give us the general direction of the zeros at infinity, sometimes the poles at infinity. So now when we are to plot the root locus, we know that there's a root locus that lies there, there's another root locus that lies there, we've drawn it in red. But these two, we know that the root locus will come, the pole at 0 will have to be pushed, the pole at -1 will also want to come to a point here where they'll now leave. But one will leave and move in the general direction of the asymptote, but not touching. It will come as close as possible, but not touching. The other one also will leave, come as close as possible, but not touching. Okay? My drawing can be poor. Please forgive that. But this is why you have computers to help you draw some of these things. Okay? So it means that that is the direction of the root locus. Okay? So generally, whatever is drawn in red is the root locus, where the pole at the origin and the pole at -1 will break away at a certain point between 0 and -1. One will go upwards, the other one will go downwards in an asymmetrical way. The pole at -2 conveniently finds a 0 at -3, so it terminates there. The pole at -4 will terminate at a 0 that exists on the real axis. Remember, the angle is 180 degrees. So it will terminate at a 0 on the real axis, but at infinity. So we don't know where infinity is. The same way, this one of the poles between 0 and -1 will terminate at a 0, which is at infinity. We do not know exactly where the point is, but we know the general direction. The reason why the general direction is important is because if I was to do a design, I will restrict my gain. Remember where the gain, where this begins is 0. The gain where each pole begins its journey, the gain at that point is 0. But as they head towards infinity, so here, the gain where it terminates here, the gain is infinite. This one will terminate, the gain will be infinity at where it terminates. The same way. So the same applies for this at -1 and at 0. So in my design, as long as I restrict my gain, so this is the maximum gain, the maximum K that I can determine. This is also the maximum K that I need to determine so that I know that my gain has to be less than that value of K. So let's say it was 20 and maybe 20, it's going to be the same. Then I know very well that all my gains must range between 0 and 20, okay? For me to be sure that my root locus is not going to be, allow the system to be unstable. Because you can see that the root locus proceeds, but towards this side, we already have instability. The root locus needs to be on the left half plane for it to be stable. So all points on the left half plane will lead to stability of the system. All points on the right half plane, even though they lie on the root locus, those poles will lead to instability. I hope that that is very clear. So the next class that we are going to have, we are going to attempt two things. One, we are going to attempt to obtain this gain K and the point. The point is known as the J omega axis crossing. So in the next class, we will calculate the breakaway point, this point that they break away from, the J omega axis, and the gain at that axis. It would be very important for us. So I'll end the class here because I see the time is up. So ladies and gentlemen, thank you very much. Time is up. Now, in regards to our C8, not the C80, sorry, in regards to the 5th year project allocation, this is what we intend to do. I know I am in charge. So what we are going to do is, one, I am going to give you a set of topics or titles, project titles that were done in the previous year by the last year students. The reason why we do that is we have to do balloting, but lecturers haven't given us their new topics for this year. But what we know is they never usually change the topics so much because they deal in the same general area. So what we are going to do is I'm going to give you a list of all the topics. You will have to pick at least, you will have to pick for yourselves at least, okay, I see our class is ending. You'll have to pick for yourselves at least 3 topics that you feel you can easily handle. Those titles are simply to guide you. They're not the titles that you're going to carry your project around. No, they're only titles that are simply going to guide you for you to know the general area of your interest and you know the lecturer that is going to be responsible for that. Now, at first, we are not going to tell you which lecturer is going to supervise that title or that topic. We are simply going to give you all the topics. You pick 3, and I'm going to do that in the first week of October. So in the first week of October, all of you will receive a list of all the titles, all the project topics. You pick any 3 of those topics. Then, once you have picked any 3 of those topics and their corresponding serial number, we are going to have a physical meeting where we are going to ballot for a topic or a title for your project. Once we have balloted, it means you will have to pick one based on balloting. We'll hope that you'll pick one out of those 3 that you had picked. Once with balloting, each student will, at least you'll fall on a topic, one of the 3 that you had picked. Once that is done, and you've found a topic, then we will tell you the corresponding lecturer who supervises that title. Then you will have to approach them and tell them that I have been assigned you as my supervisor. And so could you revise this title to be more suitable for this year? Because the title that you'll be holding on to would have been done by a student in the previous year. So on the first week, by 3rd of October, you will be receiving all the titles. I'll give you 3 days to pick them or to choose, go through them and choose whichever area you're interested in. Then either on the 14th or 15th of October, you will have, we'll meet, we'll have to physically meet, ballot, and on that day, you will know exactly which supervisor will be handling you. And of course, the title, the revised title will come from them. But at least you will have a general idea of the area of your project. So please bear with me. That is going to be done in the first week, hopefully. And then in the second week, we meet to ballot for your project. So by the end of the second week, hopefully, you will be having your supervisor, and then you can approach them. They can revise the title for you, and then you can proceed with your final year projects. Thank you very much. I will give you further updates via email. And that is why I'm delaying this, so that I receive all the emails. Some students have not even registered. So we need all the emails, because when we do balloting, we cannot do balloting twice. So all students must be available so that they receive a project allocation. If they don't, then you'll be in trouble. So please make sure that you register in good time, so that I have a full class list that then can be used for the